So to sketch a curve, I actually have a checklist of 6 very important items that I'm just going to list them out with you. Domain, intercepts, symmetry, asymptotes, intervals of increase and decrease, intervals, increase and decrease, and lastly is intervals of concavity. If you don't understand everything right now, don't worry. I'm going to explain each one of these 6 things in more detail. So I'm going to skip domain and intercepts because they're really easy to understand. The domain, where does the function exist? Where is f not continuous? Intercepts, x and y intercepts, really simple. So let's skip to number 3, symmetry. Every function either has 3 possible outcomes. 1, not symmetric, in which it's the easiest to consider, and you would basically skip this step. Even or odd. The function is has one of these 3 types of symmetry. So if it's not symmetric, that's great, but if it is symmetric, it's either even or odd. So if it's even, if a function is even, then that means for any x, f of x is equal to f of negative x. This means the function is symmetric across the y-axis. An example of this is y equals x squared. Just looking at it, you can tell it's perfectly symmetric across the y-axis. It's like a perfect mirror. And if you don't believe me, well, for all x, you have f of negative x is equal to negative x squared, which is equal to x squared, which is equal to f of x. So yes, f of negative x equals f of x for all x. So you can pick any point A on the graph, and it would have an identical f value. This should be negative A. All right, and the other possibility is if a function is odd. If a function is odd, then you would have f of negative x equals negative f of x. In this case, the function is symmetric across the origin, or 0, 0, if you will. An example of this is y equals x cubed. I should have just done y equals x, but y equals x cubed, whatever. So 0, x, y, yeah, so y equals x cubed. You can see if you were to mirror it along the origin 0, 0, it's perfectly symmetric. And if you need further mathematical confirmation, well, f of negative x is equal to negative x cubed, which is equal to negative x cubed, which is equal to negative f of x. So yes, it fits the odd function requirement perfectly. Number 4, asymptotes. For this situation, you want to find the horizontal and vertical asymptotes and the behavior as it approaches each asymptote. So horizontal and vertical asymptotes plus asymptotic behavior. Let me give you an example to illustrate this. I'm going to use this. You probably saw this in grade 12. A rational function y equals 1 over x minus 1 plus 2. It's hard to draw straight on this pen. Yeah, so x equals 1 is right here. This is the vertical asymptote, and you would draw your asymptotes out like this. And you would have a horizontal asymptote at y equals 2, which looks something like this. The function looks like this. So you find your asymptotes and the asymptotic behavior. So let's pretend we didn't learn how to draw this in grade 12. Well, then you would see that lim x approaches 1 from the negative. So for vertical asymptotes, we look at one-sided limits from the left and right side as x approaches a. So 1 negative from the negative side, for the left-hand side, of f of x, it would equal to negative infinity. And the limit x approaches 1 from the right-hand side, or positive side, f of x, it equals positive infinity. And then we would also look at the horizontal asymptotes. Now, in calculus, you can find horizontal asymptotes. Oh my god, what happened to my pen glitched there for a second. Find horizontal asymptotes. Every function either has 0, 1, or 2 horizontal asymptotes. Find HA by lim as the function approaches infinity or negative infinity. You could have 0, 1, or 2 horizontal asymptotes. So then here, if you didn't know how to graph this in grade 12, you could see f lim x approaches negative infinity of f of x equals lim x approaches infinity positive f of x, which would just be 2. Now, asymptotic behavior, so lim x approaches negative infinity, 1 of x minus 1 plus 2. I'm going to draw this in brackets. So it equals 2, but I'm going to put a negative on top. So it's slightly under the horizontal asymptote. Lim x approaches infinity, 1 over x minus 1 plus 2 is equal to 2 plus, which means it's slightly higher than 2 as the function goes to infinity. So yeah, look at, for your curve sketching, look at functions, find the horizontal and vertical asymptotes. For vertical asymptotes, find out what x cannot equal, and then look at the one-sided limits like we did here, and see if the function approaches infinity or negative infinity. For horizontal asymptotes, find where the function goes to infinity or negative infinity, and see if it's slightly above or below the horizontal asymptote or asymptotes. Number 5, intervals of increase and decrease. For this, we need to consider the function's derivative. First derivative, f prime of x. And I'm going to introduce a term here called the critical point. A critical point of f of x is when f prime a equals 0 at x equals a. When the function's derivative is basically 0, like this. And for functions, they have intervals of increase and decrease. If f prime of x is positive, at a certain interval, then the function is increasing at this interval. If f prime of x is negative, i.e. f prime of x less than 0 at a certain interval, f of x is decreasing at this interval, at this particular interval. An example I can give you is f of x equals x squared. This is super easy. I choose super easy ones right now because I don't want to make things complicated so you guys get confused while you're learning the fundamentals. I mean, this is super interesting. So, here the critical point, or CP, is at x equals 0. You can tell by looking at the graph, but you know that f prime of x would equal 2x, and that leads to x equals 0. Now, when you find critical points, you need to do a test to see if the critical point is a local minimum or a local maximum. So let me give you a visual representation of what these look like. So a local minimum looks something like this. And a local maximum looks something like this. So this brings me to our first derivative test. You can use the second derivative test, which I will explain in the last step or the next step. The first derivative test. If I used x equals a earlier, I wanted to say x equals c, but my brain slipped. The notation really doesn't matter. If f prime of a equals 0 at x equals a, this is what happens in these cases. If the function is decreasing and then increasing, so first decreasing and then increasing at x equals a, then f of a is a local minimum. I'm running out of space here. I'm going to try to do my best to fit all this in. If the function f is first increasing, then decreasing, at x equals a, then f of a is local maximum, a local max. So this is illustrating this second point here, and the former was illustrating the first one here. By looking at f of x equals x squared, we could see that this critical point is a local minimum because the function first decreases before reaching 0 and then increases after it passes 0. So by the first derivative test, x equals 0 is a local minimum for the function f of x equals x squared. Number 6, last up, we have concavity. Concavity intervals. And before I explain the math behind it, let me just give you a visualization of what concavity is so you guys have a better idea of what I'm talking about. So you have two situations, concave up and concave down. Concavity basically describes the shape of the curve at certain intervals. So concave up looks like this. It looks similar to a smiley face, concave up. Concave down looks like this. A sad face, CD. So concave up, concavity basically describes the shape of the curve at certain points and intervals. So to know what the concavity of a function is, you need to consider the second derivative. And I'm going to introduce a new term called inflection points. Inflection points. And these occur when this should have been it. I should have omitted this S. No time for grammar mistakes here. Occur when the second derivative is equal to 0. It doesn't always guarantee that you'll get an inflection point, but inflection points occur here. They're candidate inflection points. You should look here. Functions change concavity when functions change concavity at inflection points and asymptotes. And vertical asymptotes, x equals a. So we need to see if the function changes concavity or whether the concavity is the same, basically. I don't have any visual examples to show you now, but you'll see later on. And I want to talk about one more thing, and it's called the second derivative test. Derivative test. And this is your second derivative test for critical points. Critical points, which you found when you were finding the first derivative and intervals of increase and decrease, which was the last step just described. So here, if f prime a equals 0, and so at a critical point, if the second derivative is positive, meaning concave up here, then x equals a is a local minimum, which can be seen here. If there's a critical point and the second derivative is negative, i.e. concave down, then x equals a is a local maximum. And that can be seen right here, x equals a, so it's concave down here at this critical point, so this critical point is a maximum. So I have 3 examples here to illustrate the concept of curve sketching using my checklist. So the first one is an easy one. Let's start off with a polynomial. F of x equals x cubed minus 6x squared plus 9x plus 2. And let's just start off with the checklist, the domain. Easy. All polynomials will have a domain from negative infinity to infinity. That's just the way it's going to be. Intercepts. The y-intercept, just plug in x equals 0, so f of 0 will just equal 2. The x-intercept, I'm going to just tell you, for polynomials of degree 3 or higher, don't focus too much, don't waste your time too much looking for x-intercepts, because it's really not going to be necessary. But for the sake of illustrating, I just plug this into a computer. You can plug this into a computer or use Newton's method, but there's only one x-intercept, and it's roughly at x equals negative 0.2. So, yeah. That does it for intercepts. Symmetry. F of this function is not symmetric. Most polynomials will not be symmetric. Asymptotes. None. Here's a general rule of thumb. All polynomials will always have a domain from negative infinity to infinity, and they're never, ever going to have any asymptotes, ever. So let's look at number 5 now. Intervals of increase and decrease. So let's now look at the first derivative. F prime x is equal to 3x squared minus 12x plus 9. So critical points occur when the first derivative is 0, which is x equals 1 and x equals 3. F of 1 is equal to 6, and f of 3 is equal to 2. Okay, so basically, let's observe the function f prime x. Roughly looks something like this. F prime x is positive at the intervals negative infinity to 1 union 3 to infinity, and f prime x is less than 0 or negative from x equals 1 to x equals 3. So therefore, f of x is increasing here, increasing from negative infinity to negative infinity to 1 union 3 to infinity and decreasing from x equals 1 to x equals 3. Now we can use the first derivative test. I'm going to use both the first and second derivative tests in all my examples, so you guys have a good idea. You can really use either one, it doesn't matter. They're both just as good. So the first derivative test for x equals 1. F is, so you see how the function is increasing before it reaches x equals 1 and then decreases after it passes x equals 1. So f of x increases before x equals 1 and then decreases after x equals 1. So therefore, 1, 6 is a local maximum. Okay, now we have x equals 3. So if you look at the graph of the first derivative, f of x decreases before x equals 3, then increases after x equals 3. So therefore, f of 3 is a local minimum. Lastly, we have concavity. So, concavity intervals, let's look at it. So, I should have kept the first derivative. We already showed that f prime x is equal to 3x squared minus 12x plus 9. The second derivative, f prime prime x, is just equal to 6x minus 12. This is going to be quite easy to find intervals of concavity, but let's find the inflection point first. So inflection point at f prime prime x equals 0. This is where 6x minus 12 is equal to 0, or x equals 2. Or so 2, f of 2 is equal to 4, so 2, 4 is a possible inflection point. We'll see later on if it is. F prime prime x, the second derivative is negative from negative infinity to 2. Sorry, my pen glitched there for a second. From negative infinity to 2, and the function f prime prime x is positive, greater than 0, from 2 to infinity. Because the concavity does change at x equals 2, x equals 2 is an inflection point, IP for short. Now we can use the second derivative test. I already knew what my critical points were just by using the first derivative test, but hey, no harm, no foul. So for x equals 1, we had two critical points, x equals 1 and x equals 3. F prime prime 1 is less than 0. So x equals 1 is a local maximum. for x equals 3, the second derivative is greater than 0, so x equals 3 is a local minimum. And now we are ready to sketch the curve. Just plug this into Desmos, and we have everything right here. We have our x-intercept, which is roughly like 0.2. We have our y-intercept here. We have our critical points at 1, 6, and 3, 2, and as predicted, 1, 6 is a local maximum and 3, 2 is a local minimum. We have our inflection point right here at 2, 4. At 2, 4, we have our inflection point right here. The function, everything we tested about it is true. The function increases from negative infinity to 1, and then increases from 3 to infinity. It's decreasing from 1 to 3. It's concave down from x equals negative infinity to x equals 2, and then concave up from x equals 2 to x equals infinity. So everything we said about this graph checks out. I can say with about a 95% certainty that on your exam, they'll most likely ask you to sketch a rational function. So yeah, we have here f of x equals x divided by x squared minus 4. And let's go through our 6-step checklist again. Domain, x squared minus 4 cannot equal 0 because you can't divide by 0, so x equals x can't equal negative 2 and 2, so therefore the domain is negative infinity to negative 2 union negative 2 to 2 union 2 to infinity. This is the domain. Intercepts. The x and y-intercept is when f of 0. So f of 0 is just 0 here. And x-intercept, so this is when the numerator is equal to 0. That's just x equals 0. So yeah, I'll just say y equals 0 and x equals 0. There's only one intercept. The only intercept is at 0, 0, or the origin, pretty much. Symmetry. I'm just going to do this on the top. Symmetry. So let's see what f of negative x is equal to. F of negative x equals negative x over negative x squared minus 4. This is equal to negative x over x squared minus 4, which is equal to negative f of x. So this function is an odd function, therefore. Alright, no, so this function is odd, meaning it's symmetrical around the origin. Asymptotes. We have, so let's look at our vertical asymptotes first. X squared minus 4 equals 0, so there are vertical asymptotes at x equals negative 2 and x equals positive 2. These are our two vertical asymptotes. Horizontal asymptotes are when x approaches negative and positive infinity. Lim x goes to negative infinity x over x squared minus 4 equals lim x goes to infinity x over x squared minus 4 equals 0. So we have a horizontal asymptote at y equals 0. Now we need to look at asymptotic behavior. What is the behavior of the function as it approaches these asymptotes? So, lim x approaches -2. Let's look at the left-hand side first. So, lim x approaches -2 x over x squared minus 4. It's either going to be positive or negative infinity. So let's pick a really close number to -2 from the left-hand side. -2.01 over 2.01 squared minus 4. It doesn't matter if this is positive or negative, because it's x squared. So then you're left with some negative number divided by a very, very, very small positive number, which is equal to negative infinity. So this is negative infinity. Lim x approaches -2 from the positive side of f of x. So let's look at a number very close to -2 from the positive side. Let's say -1.99. -1.99 over 1.99 squared minus 4. So we'd have some negative number. And then a very, very, very small negative number here, which is basically positive infinity. So this is equal to positive, this limit is equal to positive infinity. Let's look at the next one-sided limit. Lim x approaches 2 from the negative side of f of x. So let's choose a number like 1.99 over 1.99 squared minus 4. We'd have some positive number. And then 1.99 squared minus 4 would be a very, very, very small negative number. Equals negative infinity. And lim x goes to 2 plus of f of x. Let's choose a number like 2.01. 2.01 squared minus 4. Okay, so this is basically positive over positive. So this is positive infinity. Let me sketch out these vertical asymptotes. So x equals, from -2, we'd have something like this. From the left-hand side, I'm just going to show. From the left-hand side, it would probably look like, it goes to negative infinity right here. And approaching -2 from the right-hand side, it goes to positive infinity, as mentioned here. Vertical asymptote x equals 2. So then we'd have something like x approaches 2 from the right-hand side. No, from the left-hand side, it would go to negative infinity, as demonstrated here. And as x approaches 2 from the right-hand positive side, it would go to infinity, demonstrated here. Horizontal asymptotes, x approaches negative infinity and infinity. So lim, I'm running out of space here, but lim x approaches negative infinity of f of x. It would equal, so you'd have a number x over x squared minus 4 as x approaches negative infinity. That's just x over x squared. So you'd have a very, very small negative number. Slight it would be slightly under y equals 0. And lim x approaches infinity of f of x would be equal to 0, but slightly higher than 0. So 0 plus. This is going to look messy now, but take a look at this. When I sketch the curve, you'll perfectly see the asymptotic behavior towards each of these asymptotes. Alright, number 5. Intervals of increase and decrease. We need to find the first derivative. F prime of x is equal to, so let's use the quotient rule here, x squared minus 4 minus x times 2x over x squared minus 4 squared. This is equal to negative x squared minus 4 over x squared minus 4 squared. Okay, so just by looking at this, x squared minus 4 squared, the denominator is never going to be negative. It's always non-negative. The numerator will always be negative throughout the entire domain. So, therefore, f of x, you say f prime x is negative for the entire domain of f. So therefore, f of x is decreasing throughout the entire domain, but I'm going to write it out. Negative infinity to negative 2, union negative 2 to 2, union 2 to infinity. Constantly decreasing. Lastly, we have concavity and inflection points. Let's find the intervals of concavity. So we know the first derivative. Let's find the second derivative now. F prime prime x is equal to, okay, so we have negative 2x x squared minus 4 squared, using the quotient rule once again, plus x squared plus 4 times 2 minus 4 divided by x squared minus 4 to the power of 4. This is equal to, we can factor out an x squared minus 4. So negative 2x x squared minus 4 plus 2x x squared plus 4. So now the denominator only has x squared minus 4 to the power of 3. This is equal to 2x cubed plus 8. Sorry, I made a mistake here. This should be 4x. Yeah, this should be 4x. So okay, so plus 4x cubed plus 16x. Yeah, sorry about that mistake. 4x plus 4 cubed, which is equal to 2x cubed. Oh, what is going on with me today? I am just flubbing this whole thing up. Blah, let me get my shit together. Negative 2x cubed plus 8x plus 4x cubed plus 16x. Okay, Jesus Christ. X squared minus 4 cubed. So let's simplify the numerator. our second derivative, it's good to factor this as much as possible, equals 2x x squared plus 12 over x squared minus 4. This is the second derivative. And it's not immediately easy to see where the intervals of concavity are, what the intervals of concavity are. Remember what I said this before, I'll say it again. Concavity changes at inflection points and asymptotes. We have one potential inflection point, possible inflection point at x equals 0, because this is x equals 0 is where the second derivative of 0 is 0. This is the only candidate inflection point we have. So it's not immediately obvious to see when the second derivative is positive or negative. So what I'm going to do is I am going to make a chart that looks like this. So negative infinity, we're considering asymptotes and inflection points. You're going to quickly see why I'm doing this. Alright, so the numerator, 2x times x squared plus 12. X squared plus 12 will always be positive, so let's focus on 2x. 2x is going to be negative from negative infinity to 0. And it's going to be positive from 0 to infinity. X squared minus 4 cubed. We really only have to focus on x squared minus 4. So x squared minus 4 is positive from negative infinity to negative 2 and 2 to infinity, and x squared minus 4 will be negative from negative 2 to 2. Okay, so negative divided by positive is negative. Negative divided by negative is positive. Positive divided by negative is negative. And positive divided by positive is positive. So we know where the second derivative is positive and negative. So f prime prime x is negative at the intervals negative infinity to negative 2 union 0 to 2. And it's positive from negative 2 to 0, union 2 to infinity. So therefore, f of x is concave down from negative infinity union 0 to 2 and concave up from negative 2 to 0 union 2 to infinity. And the last thing to notice is that from negative 2, 0, 0 to right here, f of x changes concavity at the origin, so therefore the origin is an inflection point. And now we are ready to sketch the curve with all this information. So I put this once again into Desmos. We see that the function is constantly decreasing throughout its entire domain. We have our asymptotes, we have our vertical and horizontal asymptotes. The asymptotic behavior is consistent with what I described earlier. So yeah, feel free to verify that. Yes. The concavity, it's concave down from negative infinity to negative 2, then it becomes concave up from negative 2 to 0, then concave down from 0 to 2, and then concave up from 2 to infinity. The origin is our only inflection point. Everything that I described is consistent with the graph Desmos provided. The last example I have here is y equals x squared minus 9 divided by x squared minus 4. I'm going to skip the process of using the checklist. When you graph it out, it looks like this. Just wanted to note some key points. We have x-intercepts at negative 3 and 3. We have the y-intercept at 0 and 9 over 4. This is our only critical point where the first derivative is 0. If you use the first and second derivative test, you'll see that x equals 0 is a local minimum. Asymptotes at x equals negative 2 and positive 2. Look at the asymptotic behavior as with the one-sided limits as x approaches negative 2 and positive 2 from the left and right-hand sides. We have a horizontal asymptote at y equals 1. And as x approaches both plus and minus infinity, it's slightly below y equals 1. The concavity intervals are from, it's concave down from negative infinity to negative 2 and 2 to infinity, and this graph is concave up from negative 2 to 2. So how do you get this graph from the checklist? I will leave the thinking to you.